Hello all, welcome. This session is about basics of chiplets and the corresponding data transfer protocol UCIe Express. Early electronics relied on bulky discrete components like transistors, resistors, capacitors, etc. Okay, so in 1958 the first integrated circuit was realized, and it was by Jock Hilpy from TI. Okay, you can see the image of the first integrated circuit. It was the upper one, the blue colored. It was I think it contained a transistor, couple of resistors and capacitors, and it produced a sine wave. The so simple was that then. Okay, but then this process of integration revolutionized the field, electronic field, packing more functionality onto smaller chips. SSI, MSI, LSI, VLSI, and more, was the direction. So SOC is one direction. It integrated entire systems onto a single die. That's one way integration VLSI field entered, ahead. Other one, the SIPs, stacked chips for increased density. Both attempted to increase the density. One SOCs was, more systems onto a single die, where SIPs multiple chips stacking. Chiplet is a new direction again. Chiplet technology breaks limitations of monolithic designs, enabling modularity, customization, and mixing technologies. One was cramming more components onto the die. Okay, so integration. The second one is packaging. Okay, let's see how the packaging technology evolved. I mean, goal is to increase the density, simple, both. These are few things I'm listing here. Okay, so what is important out of this is, in this context, heterogeneous integration, that is the second from the last. Okay, so combining diverse types of components onto a single platform, including chiplets. So it's very clear now, chiplets come under heterogeneous integration. Monolithic chip architecture, what does it mean is, you have a die, and in the same die has all the components. It's a SOC approach. Okay, all components: CPU, Serdes, memory engine, sensors, hardware accelerator, communication hardware, IOs, everything on a single die. Okay, so this has been working so good, since some time, right? But what happened now is the increased chip complexity nowadays, more functionality, more components on the same die, right? So now what's happening, because of this, yield is slowly reducing, significantly reducing, and in the recent days. And cost constraints, we cannot, there is no need for us to manufacture or fabricate every component on the most advanced node, and advanced nodes are very expensive. Okay, then design flexibility. So monolithic design limits the ability to mix and match functionalities from different vendors and technologies. For example, I have a TSMC, I have a GF, and I cannot mix and match here. One one die, one component manufactured with TSMC 16 nanometer, other one manufactured with GF say 19 nanometer. You can't mix and match here. Okay, so that was a okay. Then what is the solution here? Chiplet revolution addresses these challenges by adapting modular approach. So what is modular approach? Is the chiplet based architecture. Chiplet based architecture is the modular approach. Okay, so it has got individual chiplets and we combine the functionality. Okay, so each chiplet performs a specific function. For example, CPU core, a memory controller, IO interface, say Serdes, say couple of other things, sensors. They're all are individual chiplets. Okay, they could be manufactured in different technology nodes itself, or they could be manufactured in different foundries itself, right? Each chiplet performs a specific function, optimized. Okay, These chiplets are then interconnected on a single package to form a complete system. This is the concept behind it. Now let's see what are these chiplets. Okay, chiplets are highly specialized functional blocks manufactured as individual silicon dies. So it means in layman words, chiplet is unpackaged die. Like we used to have a discrete components, now we have a discrete dice. That's all. So these are some examples. So the chiplet dice can be smaller compared to the traditional SOC dice. Chiplet can be assembled into a package with other chiplets. Some of the examples you can see the different the chiplets are available: DSP, PCIe, display, USB 3.0, LPDDR. These are some of the examples of chiplets which are being packaged into a single package. Each chiplet is optimized to its function using the node best suited to its function. Unlike traditional SoC designs where everything is integrated under a single die, chiplets offer modular approach. We can say chiplet concept is, we can refer chiplet concept as disaggregation. See, earlier days we tried to aggregate multiple components onto the chip. In the next level, we try to aggregate multiple modules onto a single die. That's a SOC approach. Now the opposite is happening. Okay, this approach, chiplet up concept is disaggregation. It means moving the individual modules into a separate dies and then connecting in a package. See, we used to design electronics long back with discrete components. Then the very concept of integrated circuits was realized. So that led to the SSI, MSI, LSI, VLSI, etc., etc., etc. Okay, which offered specialized functionalities compared to the discrete components. It's a good revolution. Now, one more thing is happening, a good thing. Chiplets offer specialization compared to monolithic SOCs, one step above. Okay. They enable chiplets enable focusing on specific tasks, potentially leading to better performance and efficiency. See, so SIP was a good revolution, good the progress in the industry. SIPs allow combining different types of chips. For example, you can stack the chips, in a single system in package. But now one level next. Chiplets enable mixing components manufactured using most suitable fabrication process. Most suitable can be a different technology nodes, 90 and say 12 nanometer, or it could be different foundries, say for example TSMC or global foundries. Okay, and it could be MEMS also. This optimizes performance, cost, power, efficiency for different functionalities. So now we understood chiplets can be manufactured in different technology nodes, and these chiplets can be from different foundries, different vendors. Okay, and now what is this chiplet based design is, we are trying to integrate or assemble them into a single package, different chiplets. So now it's a kind of a heterogeneous integration. So it comes with their own their own challenges. Some of the challenges are interoperability and testing and verification. So why interoperability? Because different vendors, different standards, how to communicate with each other, talk to each other. Why testing and verification is because a new field, a new domain. Our tools may not be good enough to do the thorough verification of it. So what are the solutions? Naturally, go for open standards so that everyone, every guy, every industry, develops their IPs, keeping these protocols in their mind. Open standards. One such is UCIe Express, Universal Chiplet Interconnect Express. Other one is develop your EDA tools, make them more matured and streamline the design and verification process of chiplet based systems. So heterogeneous integration is not involves day-to-day communication. It means chiplet to chiplet communication. It in other way we say day-to-day interfaces. Let's see what are the challenges and solutions. So connecting chiplets on a single package requires high speed and reliable communication channels. Do we have it? And within the package, space is limited for interconnects. How do you handle it? Maintaining signal integrity at high speeds across short distances poses challenges. How do you handle this challenge? Okay, what are the solutions then? Let's see. So adopt advanced packaging technologies, techniques like silicon interposers and advanced organic substrates. Develop such things for efficient and reliable day-to-day communication. And of course, people are using Serdes high-speed signaling protocols like Serdes, for high-speed communication. Now we learned that we can assemble multiple chiplets into a single package, and we can connect them using different packaging technologies like interposers or organic substrates, etc. We can connect. Then how do you communicate? How do you send out the data? You have to come up with the protocols. Let's see. And these protocols can be broadly classified them into proprietary protocols and open standards. So we have no clue what are those proprietary protocols. Let's not go there. Coming to the open standards, I'm listing couple of well-known open standards for chiplet to chiplet communication. One is Universal Chiplet Interconnect Express, UCIe Express. Other one is AMBA CHI-C2C. The third one is OCP CDX. These are well-known open standards for the chip communication between the two chiplets or two dies, or communication within the package. Let's compare UCIe Express with other relevant protocols or models. Okay, what is UCIe? Universal Chiplet Interconnect Express, UCIe Express. It's a prominent open standard aiming to establish a ubiquitous on-package interconnect for chiplet-based systems. So UCIe consortium, right? So UCIe consortium is backed by the foundries like Samsung, TSMC, and IP design companies like AMD, ARM, Qualcomm, etc. EDA companies like Cadence, Synopsys, and other guys like NVIDIA, etc. So it's like pretty much big guys are backing this UCIe consortium. So UCIe defines both physical layer as well as the protocol layer. Okay, for high speed data transmission. Okay, that's all, right? So let's just for comparison's sake, I'm placing the OSI model, which contains 7 abstract layers from physical to application. Observe this, what's happening. Except physical, most of these the layers have their own protocols well defined. For example, application layer as a HTTP, FTP, etc. Whereas the data link layer as a Ethernet, point-to-point, LAN, etc. Of course, physical layer may not have its own the protocols. Okay, so now let's see where is our UCIe and PCIe fits or compares with these protocols related to the OSI model. Okay, PCIe and UCIe operate at a lower level of abstraction compared to the OSI model. It means, so this PCIe UCIe operate at a lower level of abstraction. Physical layer is the lowest level, abstract level, right? Abstract layer in the OSI model. This PCIe UCIe falls further lower level of abstraction compared to the OSI model. So now let's also compare PCIe with UCIe. PCIe, why PCIe? It is a traditional data transfer communication protocol from the era of monolithic monolithic chips. Okay, so PCIe is application is interboard communication, whereas UCIe is intra-package communication. So UCIe is mainly developed to establish the communication between two chiplets or two dies, which are assembled in a single package. It means intra-package communication is what is the goal of UCIe, whereas PCIe is interboard communication, board to board. Assuming, okay, so PCIe connects peripherals from to CPU on motherboard, whereas UCIe connects chiplets within a package. So UCIe is a relatively a new standard, and it's based on PCIe physical layer and CXL protocol stack. So it's UCIe is optimized for short distance, high bandwidth on package communication. Okay, it's a high bandwidth on package communication. Let's in 2 minutes compare our UCIe where it fits with respect to the ODSA layered communication stack. See, ODSA layered communication stack is also a layered structure. You can see them here. UCIe doesn't directly map to any specific layer within a ODSA stack. This is one takeaway. Instead, they are complementary. They play the complementary roles. Okay, so UCIe offers standardized solution for efficient communication within a chip, contributing to building high performance SoCs used in data centers. Whereas ODS stack, right, they provides broader framework, very similar to OSI model, okay, for interoperable communication across various network elements within a data center, including SoCs utilizing UCIe technology. I am trying to list a few interconnect standards used for data transfer. For example, peripheral interface standards, interconnect standards, PCIe, USB, SATA, Thunderbolt. These are some of the interconnect standards, okay, for data transfer in peripheral interfaces. Similarly, on-chip and network communication purpose, okay, the standard for it, okay. AMBA is a on-chip, interconnect standard for data transfer on chip. Similarly, Ethernet, Wi-Fi, InfiniBand, they are used for network communication standard. So some more emerging and specialized interfaces, okay, are UCIe, CXL, NVMe, MIPI. Like many interconnect standards, UCIe also builds upon a layered architecture similar to the OSI model or even ODSA communication stack. But UCIe layering is specific to chip communication. So these are the UCIe protocol stack. You can clearly see 3 layers: protocol layer, die-to-die adapter, and physical layer. What physical layer does is it defines electrical characteristics of data transmission between chiplets. Okay, it specifies things like electrical engineering, electrical signaling like voltage levels, data encoding, data rates, the lane configurations, signal integrity, error correction mechanisms. This is more of a circuit level thing. Okay. Day-to-day adapter layer acts as an intermediary between physical layer and protocol layer, manages the link between chiplets and handles functionalities like link initialization, parameter negotiation, error handling. And the third one is the protocol layer, determines how data is formatted and transmitted between chiplets. UCIe allows flexibility by supporting multiple protocols such as PCIe, CXL, and proprietary protocols. If we ask us as an analog or interface circuit designer, maybe we fit more into the first physical layer. Out of 3 UCIe layers, let's look into UCIe PHY physical layer. This protocol, UCIe Express, is developed as a standard for communication between two chiplets or two dies, die A and die B. Okay, so from one die to the other die, you can use parallel wise for the transmission of data, or you can use Serdes for the transfer of data. Then let's see what is this phi or die to die phi. Okay, the physical layer. So the upper one is the block diagram of the physical layer of UCIe PHY architecture. If you see, left side is a serializer, right side is a deserializer. In the left side is transmitter, receiver side is receiver, in the simplest words. So in addition, we might need the clock circuits, okay, of different phases. We might need additional the equalizers, left and right. We might need power supplies. So many other things are required here. Okay, otherwise that is a simple black diagram of the UCIe PHY. In other words, the Serdes. Let's see how these multiple chiplets are physically connected. Okay, there are a couple of ways, advanced packaging technologies which provides us the ways to connect different chiplets, physical connection. One of them is an interposer. You can see that, right? So in the image left side, it is a dedicated silicon substrate with routing channels. Don't confuse them as a bias. It's a routing channels, but it's a dedicated substrate itself. Other one is a direct bonding. It's a physical connections like traditional way, copper to copper bonding, joining the chiplets. The other one is the embedded bridge chips. These are small silicon chips integrated within the substrate and connect them. Okay, so some people use a combination of direct bonding and embedded bridge chips which give rise to the EMIB. And the TSVs, through silicon vias is one way to connect the two chiplets. Okay, these are the vias etched through silicon substrate of a chip, allowing 3D stacking of the chiplets. There is other way, package on chip, and it's outside the package anyway, communication. Stacking multiple pre-packaged chiplets, like chip stacking like that. Okay, pre-packaged chiplets on a top of each other, connecting using solder balls or micro bumps, etc., etc. First four are literally we are talking about chiplets and packaging a single die within a single die. So combination of this can exist. Now, before closing, let's connect Serdes or UCIe to some of these circuits. Okay, in this example, I'm taking the IO circuits or interface circuits. IOs can be so many types. We have a HSL, SSTL, LVDS, and GPUs, MIPIOs, n number of things. Okay, I2C, I3C. So, what are those IOs or interface circuits which are used in Serdes? Let's see them. I'm considering transmitter now. Okay, or serializer part. First one is SST driver circuit. It means source series termination driver circuit. The very related IO circuit is SSTL, stub series termination logic IO. Their concept wise they are very similar. So what is this? Source series is, see, the driver side is we call it as a source, the receiver side we call it as a left. Source side is a near end, the receiver side is far end. Driver side is a source, other side is a receiver, we call it as again, right? Source series. Look at the 18 ohms resistance or sometimes 50 ohms. It's a programmable anyway. Okay, these are in series with the source, and hence the source series termination of 18 ohm is a termination resistance, series termination with respect to the source. So that is a source series driver circuit. It's a kind of a transmitter or IO used, okay, in the serializer part or transmitter part of the Serdes. Okay, the second one is very similar to the LVDS, where we have a underdome termination. Receiver head is also underdome termination, and a differential logic, low voltage differential signaling, the where output voltage differential signal is maximum is limited to 400 millivolts with output command of 1.2 volts, and depends, maybe in different technologies different things. Okay, so this is one of the LVDs can be used as a driver or transmitter in the Serdes. The other one is again CML logic, where you see that, right, very similar to the LVDs. Is also low voltage differential signaling. Termination really matters here also. Yeah, these things. These are the three architectures. We can list some more maybe, but these are predominantly used in Serdes for a transmitting part of it. Again, let's look into the receiving part of it, the pad connected to the receiver, right? So we expect signals reaching the pad or the input part of the Serdes is very weak, especially because of band limited channel. We might need the equalization. So generally we start with the equalizer uh, uh, at the first part of the receiver, then we do the remaining part of it, deserialize and later. Okay, so other than these things, because it is high speed receiver termination, this is Serdes is a very high speed data transmission, right? And the signals are coming from outside world, like between chiplets, right? So termination really matters here. The proper termination is important. And if it is connected to the external world, we definitely need a serious EST production scheme. Our regular old style may not work because it's high speed signals. You should not attenuate it, you should not be a load for it. Thank you for your interest. These are some basics about UCIe and chiplets. Let's see if we can do some more real MOSFET based circuits in the coming days.